Buonasera, benvenuti a
Good evening and
GiovedìScienza,
welcome
benvenuti a coloro che ci
to
seguono
GiovedìScienza,
web
Science
in
on
rete.
Thursday,
Ora
and
incominciare
welcome
questo
to those who
incontro
are following us
da
online. I'd like to
qualche
start
pagina
this
di questo
meeting
libro di cui
today
tra poco
with a few
parleremo
pages
e vediamo se
of
riescono
this
a
book
inquadrare
which we'll
questa
be talking
pagina.
about. And
C'è
I
scritto
don't know if you can
radice
see
di
this,
2
but
uguale
here it says a square
1,41
root of
e poi
2,
altre cifre decimali. Da
1.41,
questa
and then
pagina che
other
vedete è
decimals.
fatta
All
di
this
cifre
page, which you
decimali
can
che vengono
see,
dopo
it
quell'1
consists
e il
of the
41 e il
decimals that
valore
come
di
after
radice di 2.
the
Ma poi si può girare
1.41,
pagina e
which
si
is
trovano
the
altre
value
cifre
of the
decimali,
square root of
poi
2, and
altre
then it goes
ancora,
on page after page.
e poi altre ancora.
And
Vi
again,
chiedo di imparare la memoria naturalmente, ma
I'm
qui ci
not
si ferma,
asking you to learn them
ma
by
si potrebbe
heart,
andare
but
avanti, si
this
potrebbe
is where
andare
it
avanti
stops. But in fact, it
all'infinito
could go
senza
on and on and
trovare
on
una
and
legge
on
che regoli la
forever and ever
successione di queste
without
cifre.
finding
Ecco,
a
parleremo di questo stranissimo
law
oggetto che
that will
viene usato naturalmente,
regulate
però è
these
uno degli
number
oggetti
or that
strani
governs
di
these
cui è bello
numbers.
raccontare
We'll
la
be talking
storia in
about this. It's
matematica. La
very beautiful
radice
to
di
talk
2.
about the history of this in maths,
È uno
the
studioso in
square
particolare
root
dei sistemi
of
dinamici e della
2.
teoria dei
Benoît
numeri.
Rittaud is a
Il suo lavoro
researcher
nella
at
diffusione
Paris
però della cultura
13, at the
matematica è
University of Paris
altrettanto
13,
importante.
and in
Avete già
particular,
sentito
he
alcuni
studies
titoli che sono
dynamic systems
tradotti in
of the
italiano,
theory
poi
of
ce ne
numbers.
sono
His
parecchi in
work to
francese. C'è un
popularize
suo sito
mathematics
molto bello
is
che
very
potete andare
important.
a
You've
vedere.
already
Per molti
heard
anni ha
about some
condotto
books that have
in questo
translated into
sito
Italian,
promenade
and then there's some
mathématiques,
in
le
French.
passeggiate
There's his
matematiche.
website, which is
L'ha
very
fatto credo per 6
interesting.
anni,
And for
adesso
many
ha lasciato
years,
forse
he
un po' di
managed
lato.
this site, Promenade
In
Mathématique,
particolare vorrei
that is
anche
to
ricordare
say,
la sua attività
walks
proprio
in
pubblicista,
maths.
cioè sui
He
giornali
started
e sulla
that and did
recherche.
it for
È
6 years, and now
il
he's
mensile
passed
di scienza francese
the baton to someone
più
else. And then
diffuso ed
he's
è
also
un
been
mensile
writing
veramente molto
on
molto
the
bello.
subject
Così
in
come è bello
papers
questo libro,
and
La favolosa
on
storia della
La
radice quadrata di
Science,
2,
which
che
is
ha vinto
a
il premio
very
Peano. Io credo
well-known
che
French
molti matematici
monthly,
vengano
just as this book,
volentieri a ritirare il premio
the
Peano.
fabulous
Sì, perché c'è una
story of the
bellissima
square
lista
root
di
of 2, which
predecessori,
won
ma
the
anche perché un
Peano
bellissimo
Prize. I
nome,
think
proprio
that
Peano
many
è un bel nome.
mathematicians
Peano,
come
ricordiamo,
for
un
the
grande
Peano
matematico
Prize,
della
not only
nostra terra,
because of the
nato
people
nei
who've won
pressi
it,
di
but
Cuneo,
because it's also a
negli
beautiful
anni
name.
iniziata la
Peano,
famosa cura
let
di
us not
Peano,
forget, was
che
a very famous mathematician who was born near
la
Cuneo,
mamma
near
dei
Turin,
frattali
and the
e
Peano
poi
curve
ha
is
fatto
named
tante
after
cose, tra
him,
le quali anche
which
l'invenzione di una
he
lingua
discovered and
artificiale, un
which is
latino non
probably
declinato,
the
perché
mother
era
of
nato da una visione
fractals, but also
universalistica molto
many other
interessante
things,
anche dal punto di vista
including
politico.
the
E io che ho
invention
cominciato
of
la
an
Gazzetta del Popolo vorrei
artificial
ricordare che
language,
sulla Gazzetta del
a
Popolo
Latin without
Giuseppe
any
Peano scrisse un
declensions, because
articolo
he
nel
had a
quale sollecitava
universalistic approach,
il
even in
rafforzamento
politics. I
dell'Istituto
used to write in the
Internazionale
Gazzetta del Popolo,
Sopranazionale Comune
and he wrote
Nazionale.
an article
Quindi
in
avevo
that
una
paper
visione anche
many years before
politicamente
me, but
molto
where
molto
he
interessante.
maintained the
Chiedo
fact
scusa se
that
ho
there
parlato
should
via molto
be an
tempo, la
international
parola al professor
institution
Benoît
like the
Rittaud che ci
United
parlerà
Nations.
appunto della
So,
radice di 2, una
he
storia
had a
come
very
proprio di origine
interesting
molto interessante.
vision.
Prego.
Please excuse me for having taken up so much of your time. And now Benoît Rittaud, who is going to be talking about it. The floor to you, sir.
La physique a ses constantes fondamentales, comme la vitesse de la lumière ou la
Physics
charge de
and
l'électron.
its constants, such as the charge of electrons or the speed of light, is well known and
Et en
studied.
mathématiques aussi, il y a des constantes
And in
fondamentales.
maths, too, there are
On pense
fundamental
plutôt aux nombres
constants.
en général, ou au
We
nombre
think,
d'or,
for example,
et quelques autres quand
we
on est
can
un peu
think
plus
of
savant.
various ones.
Et
When you study, as you go on, you acquire more of them. But
est un peu
paradoxically,
méconnu.
the square root of
Elle est
2
citée
is
comme
not
exemple,
as well known as it should be. It is often given as an
cas
example,
particulier intéressant pour certaines mathématiques,
as a
comme cas
particularly
particulier
important
historique,
case
ou-
for some maths, for some historical point of
En
view, and then it
réalité,
is
la racine
forgotten.
carrée de 2 a un
In
intérêt
fact,
pour au
the
moins
square
trois
root
raisons.
of 2 has
D'abord, une dimension
is very important
mathématique
for three reasons. First of all, a mathematical reason in itself,
culturelle qui va bien au-delà des
then
seules
a
mathématiques.
cultural reason which goes well beyond the mathematical problems, and lastly, a historical framework which is quite unique in the history of maths.
Et c'est par cette histoire que je voudrais commencer.
And it is, this is what I would like to start with, point 3, showing you this Babylonian tablet, which was written, I think, about 4,000 years ago. It is the work of a student who was studying to become a scribe in Babylon. and it is clay, and also you can interpret it quite easily. You can translate quite easily, because unlike other tablets of the time, it isn't written in a language that we don't understand or don't know. It is written in a language which is the most universal language on earth, which is the language of mathematics. And I think it would take about 10 minutes at the most to translate this, or to get you to translate it. But since we haven't got 10 minutes for that, I am now going to give you the answer or the translation of it. The tablet shows a square, the two diagonals, and a certain number of signs which can be seen, and they correspond to numbers, which are written in the Babylonian system of numeration. Just with these figures, we can recreate what, or retrace what the student did 4,000 years ago. Probably, what was the question the student had been asked? What you would notice that if you multiply 30 by 1.4142129, you get 42.42, etc., etc. That's the first comment. And the second comment is that 1.4142, etc., corresponds to what we call the square root of 2. It is the number which means that when you multiply it by itself, you obtain the 2. The student had to answer something like this. Given a square whose side is 30, determine the length of the diagonal. And first of all, what did the student do? He or she probably made a nice drawing. 30 was the side of the square, and it was multiplied. I value 30 by this constant, which is 1.4142129, etc., and that gives me 42 point, etc., etc., which is the length of the diagonal. Probably got a good mark, because the answer is right. However, you can see that this tablet is not very important in itself, but it is an opportunity to rethink. And in answering the initial question, there were a number of other questions that could be and probably were raised. Right? We understood what the tablet did, we understood what was done there, but then we still have an open question, because there are at least 3 question marks that have to be addressed. The first one is how did the scribe know that there was this relationship between a purely geometrical shape, a square, and it's a diagonal, and the algebraic value of it, that is to say, the square root of 2, the number which multiplied by itself will give you 2. There is no link, apparent link, between the two. In spite of that, the relationship exists. The second question, once that we know it is the square root of 2, the number which multiplied by itself, how do you work on it? Well, here the tablet gives a value which is accurate at least 6 digits after decimal digits. The 9 is not correct, but it is the problem of the translation or transliteration I gave, because Babylonians had a base 60, while we use a base 10, and translating it from one to the other, there may be some slight discrepancies. So instead of 9, there should be a 6, which, however, is still incredibly accurate. And the question is, how did they manage? I think that that it is the number which has been known most accurately in the past 2,000 years. I don't think that any other number has been calculated in an equivalently accurate one before, let us say, the Indian tables in the Middle Ages. And last question, what's the use of it? Why would a Babylonian be interested to know what the figure was 6 decimals down the line? Well, to be honest, we don't know. We can't answer any of these three questions, the last ones I raised, because the tablet is something we found on its own. We have very few theoretical documents or books. So all we can do as it would be to imagine and not and reinvent, really, not rediscover, but reinvent. Let's go back to the first question. How do you create the link between the diagonal and the square root of 2? The oldest text that we have is not Babylonian. It's a text which is Greek and which goes back to Plato. 4th century BC, but in one of his dialogues, Plato gets Socrates to discuss with a slave who has never been to school, does no geometry, and the aim of Socrates is to prove that even the slave has in himself the resources which would make it possible for him to find something that to help him understand this. And to illustrate this Socratic idea, the discussion which there was between Socrates and the slave was a discussion on the doubling of a square. The question was the following. Here is a square, and you're asked to build a square which is twice as big. Twice as big in terms of its surface, so doubled surface. The slave doesn't fully understand what is being asked and makes a number of suggestions. Suggests the size of the side could be bigger, and then they went on discussing it because that would make it 4 times as big. But the answer which Plato gives is that you have to trace the diagonal, use it as the side of the next square, and Plato says this green square is twice as big. Why? Well, because here, this is it. You can complete this figure. The figure has 8 triangles, 4 and 4, the yellow and the white, all over the same side, the same surface, and they have sides which are equivalent. So you see there are 2 triangles in each square, and the green square contains 4 of these triangles. Thus, it is twice as big. I think that it is difficult to make it any simpler. You don't need to know any geometry about it. All you have to do, you have to be able to count the triangles. There are 4, there are 2, there are twice as many, and so on. Therefore, the green square is twice as big as the other one. After the discussion by Socrates moves on. But as far as we're concerned, that result shows that the diagonal is related to the square root. Why? Well, because if, say, the initial square was 1, had a surface of 1, if the side of the initial square is 1, we can show you that the green one is 2 because it's twice as big, and the side of 2 is the square root of 2 because the surface is the side by the side multiplied by itself. Here you see it moves on to the surface. The second question is, how would you calculate the square root to the decimals? Here, we have to go back to what the Babylonians said. I am not going to go back to their discussion, but to the mathematical equivalent. We're going to play a game. Say we have a rectangle here, which is 1 by 2. And we're going to modify the sizes of this rectangle so that it will look more and more like a square without changing its surface, which in any case would be 2. If we have something which is very close to a square with a surface which is close to 2, the side will be roughly the square root of 2. 1 is too small, 2 is too big, you can see that, and we're going to take a value which is in between. What is the simplest in-between value that you can calculate between 1 and 2? It's 1.5, or 3 halves. Small exercise, which I'm going to let you solve on your own, which is not difficult. A rectangle with a surface of 2, with a side which is 3 halves, will have the other side which is 4/3. And this looks much more like a square. In other words, 3 halves and 4/3 are better approximations of the square root of 2 as opposed to 1 and 2. And you can see it very clearly. Now, of course, we haven't really got a square. Say we want to improve things a little bit more. Well, you start again with a new rectangle, which again 4/3 and 3 halves. Well, we'll have an average. Try an exercise which is not difficult. The average between the two, or the mean, is 17/12. And a rectangle which has a 17/12 and a surface of 2 has to have 24/17 in the other dimension. Here you can't really see the big difference with a square, which it means that the naked eye cannot perceive the difference between 24/17 and 17/12 and the square root of 2. This method is very effective if you wish to have an approximation of the square root of 2 or other square roots. There are 3 main advantages. The first is that it's very, very simple. If you write the calculations and everything, it's really a very simple exercise. The second advantage, which is visible here, is that it's very fast. If you write the decimals, which you will have here, you'll have an approximation which is in excess and in the exact figures double at each step. Twice as many decimals at each step, whether in excess or by default. And last advantage, a bit unexpected, is that it's self-correcting. That is to say, if you make a mistake calculation, instead of saying 17/12, you say 19/12, for instance, you'll have another rectangle. It will be the right one. But if you start again working out other rectangles, the error is going to get smaller and smaller, and you will come closer to the square root of 2, unless you make mistakes repeatedly. But if you don't make too many mistakes, it's not bad. I don't know if that's true in Italy, but in France, until the 60s, another method was used at school, which was very complicated, very slow,
autocorrectrice, qui ne se corrigeait pas du tout.
and did
Pas le
not correct itself alone.
Jusque dans les années 60, c'est pas vieux.
It was not self-correcting
C'est
right up to the
seulement les
60s, not so
calculatrices
long ago.
électroniques qui ont remplacé ce
It's only with the
alors qu'il y a
electronic
4000 ans,
calculators that we have been able to replace it. But 4,000 years ago, they already knew how to use this very effective method to reach the square root of 2 by approximation. It was so effective that we have still not been able to develop anything better, in spite of all the transformations and changes in the way in which we calculate, especially since the discovery of computers. We haven't been able to improve on them, while we have changed all the rest of things. But for the time being, it's the oldest method and it's still holding on 4,000 years down the line. Another question which was raised by the Babylonian Tablet is what's the point of knowing the square root of 2? What's the problem? What's the advantage in calculating all those decimal figures? Well, one possible explanation comes from architecture. Although there is no evidence, there is some evidence in Egypt. Imagine that you would like to build a very big square building, for example, of the size of this theater. How are you going to manage to lay the foundations? Well, you could take, I don't know, a piece of rope and outline a square for the first 2 points. Then we can have a square angle and then reach another point, which is another square angle, and so on. And lastly, you have the 4 points, and you will have to test whether the length is the right one. But even if the sides are the same size, you're not really sure that you have a square. You could have something like this, which is like a diamond D shape. Here you see, instead of being 90 degrees, it's 82. And here you have 88 and 87. 2 or 3 degrees is not much, but you can imagine what the impact would be in a building. Clearly, you can say that it's very obvious that it's not a square. But in fact, you must remember that you're not only making a drawing here, it's something very practical. And here you can see things as if from above, as if you were in a helicopter. In fact, here you have a 10-meter square. You can see it, and maybe you can rise a bit above it, but you get a bird's eye view. But our eye is very good at telling horizontal from vertical, but when it's no longer horizontal or vertical, it's very difficult for our eye to perceive it. Let us take these 4 diamond-shaped or shapes. Only one is a square. Which one? Maybe it's not quite clear because there's a slight deformation, but would you like to vote? Top left, raise your hands. About a fifth or a sixth of you. Top right.
À droite. Celui en bas à gauche.
Bottom left.
Un peu plus.
Few more.
Et enfin, tout en bas à droite.
And lastly, bottom right.
Un peu aussi. Qui ne sait pas? Ah, donc vous avez tous voté.
Well, anyone who wishes to abstain?
C'est pas mal, bravo à l'assistance dans son ensemble.
Very good.
Qui a plutôt bien
Very
trouvé,
good, because it was the bottom left.
Pour le bon.
There was a relative majority for the right one, meaning bottom left. It's not as clear as it is on the vertical ones which I was giving. These are all a bit mixed. And it is a constant problem in architecture in practical terms, at least up to the Renaissance. How can you draw or a right angle? Many methods were suggested. Many of them were mathematical models. Many worked better than others. But until we see that the one which was used by the Egyptians was that of tracing the diagonal. And if this corresponded to the square root of 2, then that meant that it was a right angle. Now, why did the Egyptians do this? Well, they had a system to measure which was called the digital system. Digital because the smallest unit was the finger. And the orders of magnitude which followed of this system were probably approximations of the square root of 2. Currently, our orders of magnitude are by a factor of 10. You go from millimeters to centimeter multiplying by 10, and then to decimeter multiplying by 10, so on and so forth. Instead of multiplying by 10, the digital system of the Egyptians multiplied by a figure which was an approximation of the square root of 2. It's not sure. What I'm saying is just a hypothesis which was suggested by an Egyptologist called Francis Griffiths. And even though we can accept it as viable, this use of the square root of 2, it does not really answer the initial question, because the Babylonian tablet gives a precision or accuracy up to 6, 7 digits after decimal digit. Imagine an enormous building on a square with a square base, which you might have built in Egypt, for example, a pyramid. The largest of all pyramids is about 250 meters in each side. And if you imagine that you need to know the square root of 2 with more than 6 decimals, that means that this pyramid is something you're going to build with an accuracy of a millimeter. It's too accurate. It's too accurate. And in fact, you can have a 3–4% leeway, which is present in all the history of architecture before the 16th or 17th century. So too accurate. So we can also try to find other practical implementation of the square root of 2. You can find them. But basically, never do they require many decimal figures. However, one has to think that the interest was focused elsewhere. Clearly, this was important, and we have to answer this question because we have no documents to prove or indicate one or the other. So we have to do a bit of guesswork. Question that may be raised when you write the first decimals of the square root of 2 is these decimals coming to an end. You can imagine, for the sake of the argument here, that the people asked this question, or asked themselves this question, because they knew that the square root of 2 was a fundamental constant in geometry, and it's the relationship between the diagonal and the side of the square. They had the first digits after the first decimal digits, and then it went on and on and on and on. So this raised the question whether the square root of 2 is a decimal number or not. That is to say, is there a finite number of digits or decimal digit? That is to say, is there a last figure, which I have put as D here, which would terminate, so to speak, the numbers of the square root of 2? Is this possible? Well, One method is that obviously you can multiply the result of the square root by itself in two different ways. On the left here you see the theoretical manage, which if you multiply the square root of 2, by definition it gives you 2. Fine. But then on the right, how could we manage to do it? For example, we don't know when it's going to finish, how many decimal figures there are. So one wouldn't know how to calculate it when you do it at school, multiplying, just as you learned how to do. But we could also have one idea on this type of calculation. That is to say, what is this calculation? Given that the final result has a figure which is to the far right, which I'm going to call U or name U. It is the total of the digits of d times d. So d times d, d multiplied by d, gives me the figure of the units. I continue all the calculations that I wish to, but the first figure which I wrote, the d times d figure, will be also included in the final result, as is. This is a very important idea because we know that the final value which we have to obtain is 2. So this figure, which is u, which is all to the right, must be equivalent to 0. It's a decimal one, and it must be 0, because otherwise you won't get 2 as a final result. We also know that if the square root of 2 were to stop and were to have a last digit or figure d, then d times d is 0, which gives a very simple way of knowing how to calculate d. d is a figure between 1 and 9. Which one could it be? If I take d, or multiply 1 by, if d equals 1, then u equals 1. So it doesn't work. So d can't be that. If d equals 2, then u equals 4. And 4 doesn't work. 3, then 3 3s are 9, 4. 4 4s are 16, and there is 6 as the last figure. And then if you continue with all the other figures, then you see that it's never 0. Ouch. There is no figure that corresponds. Of course, you could say we could take 0. 0 times 0 is 0. But clearly, when you write the square root of 2, the last decimal is never 0, because if it were 0, we would have to work differently. So there is no possible last digit or last figure. In conclusion, there is no last figure. It never stops. You can write, if you write the approximation of the square root of 2, there is an infinitely large number of figures. There are decimal figures. This result is a particular case of a more general case, which is the fundamental theorem on the square root of 2, whereby we say that it's an irrational number. It is not the division of a whole number by another one. You can't write it as a fraction. You say that it is an irrational number. That's what it's called. There are very many ways of proving this theorem, about 20 of them. You can generalize what I did, base 10. There are a number of other methods. I will be giving you another one if I have time later on. But I am not now going to talk about this mathematical theorem in detail, although in itself is an interesting history. I'm going to talk about the more cultural side of this result and its importance. To understand it, we should once again write history and go back to the school of Pythagoras. The school of Pythagoras was a school which pieced together very diverse, irrational, in fact, if we want to go back to that word, objects, but its slogan was that everything is a number. Everything is a number, which for this school means that everything can be expressed through numbers. It's a very modern idea. It's something which we could say everything is an equation today, or everything is a differential equation, or everything is a physical system. But the idea that they had was that it was a means to study the world through mathematics, although for them it was a little different. It was something a bit different. It was mixed to a number of different things, numerology, so on and so forth. This fundamental theorem, this idea that everything is a number was justified by the theory of harmony of proportions. In this the school of Pythagoras, they had noticed that if you took two chords of a musical instrument, where one is twice the size, the length of the other, then the sounds that these chords produce are basically in a musical interval, which is the octave. If the longer chord, for example, plays a C, then the shorter chord will play a C in the upper octave. If the first chord measures 3 and the second measures 2, then you have a different ratio, that is to say a fifth, and you have C and G. The ratio is 3 to 3 halves, and this is the relationship of an expression between numbers. It's the 3 to 2 ratio, while the other one is the 2 to 1. So sound is numbers. And for the followers of Pythagoras, this was true everywhere. It's true for the universe as a whole, because again, the universe was a numerical relationship. The idea is viable because it works for chords, but it also works with vases full of water. It also with the thickness of metal discs, and every time we can verify that the fifth or the octave have that sort of ratio. We also then understand with that the theorem of the square root of 2 raises an issue, because the diagonal of the square cannot be found, or at least we cannot find the whole numbers to describe the fifth of the octave and so on. The diagonal of the square doesn't come under this system. So there was a mythology in which suggested that they were destroyed by this result, and that all the mystics' ideas then fell to the ground. That's a bit romantic, but if you talk about proportions, that's important. The idea was quite successful, in particular in art and even in architecture. I'm a bit ashamed to talk about it in Italy, because a lot of people know more than me on these issues. But during the Italian Renaissance, and just before it, and before Alberti, the architect was an artisan rather than an artist. And it is thanks to Alberti that things are changed, because he wants to be considered as an artist, and therefore he creates a theory of architecture, and was not simply the person who could produce a square angle or make mortar. He had this idea of the harmony of proportion, which was a very interesting idea, because in fact when you build a facade, you want it to be well proportioned, and that the height to width ratio should be harmonious. Alberti, in fact, imported the words from music, from the world of music and mathematics, to create an architectural theory. Since he drew inspiration from Pythagoras on the ratio between and among numbers, there was no irrational number in architecture. In his idea, there is one exception, and I'm sure you can guess which one, and that's the square root of 2 in architecture. For instance, this is an extract from a French translation of Alberti's fundamental book on architecture, where he's particularly interested in how to calculate the size of a door, so that a given door should be neither too low nor too wide nor too high. And he thinks that the widest possible and the greatest height is when the height is twice the width of the door, which he represents here, inscribing 2 circles inside the space to say that the rectangle is twice as high as it is wide. The opening of the door, if it has to be the lowest possible, he says, although he doesn't use the same words, that the height has to be at least the square root of 2, and he shows this by tracing a square on the base of the door and having a diagonal and explaining that he is going to use the length of the diagonal but vertically, so it is the square root of 2. Here, this is the use of the square root of 2 in architecture, which is completely different to the one which the Egyptians might have implemented, because at the time it was a technical use, while here it answers some aesthetic issues going on to Alberti, but they suggest that the square root of 2 should be used as in aesthetics, and it's an exception to the other theory of architecture, because, as we know, the square root of 2 is an irrational number. Another example, which came much later with Sebastiano Serlio, who shows the 5 orders, the various columns, the Corinthian, the Ionic, and so on. And he also is interested in the pedestal of all the columns, which is a rectangle, and he suggests, according to the orders, that there has to be a particular different ratio. These ratios are rational ratios. For example, for the left one, it is a square, while for the one to the far right, the composite or mixed column is different. And you see then there are 3 halves, and the second one, the Doric, it says, you can't really see it from here, but it says proporzione diagonale, which means diagonal proportion. It's a nice example how you can have the square root of 2 in the middle of more rational approaches. More recently, at the end of the 20th century, you have here sculpture by a French artist, who is called Michel Vendron, and which is called the Door of Harmony. The Door of Harmony, or the Gate of Harmony, is at Mas, close to Geneva, and it is a rectangle which is built with in mind the square root of 2, or calculated with the square root of 2. So here we have the Renaissance, but this brings us to another issue, that is the golden ratio. There is a bit of a myth that it was used a lot in the Renaissance, and a number of other situations. There's a bit of a mystique around it, but in fact there is no trace of the use of the golden ratio at that time. It was much later. The mythology will be mixed with the architecture itself, and it is a story which is very interesting in itself, but more generally there was no reason to use it, because it is an irrational number. And in the Renaissance, they didn't really use irrational numbers because they're not very useful, except for the square root of 2, which is very comfortable because it's simply the diagonal of any square. This
Michel Ventron a appelé cette
here.
porte d'harmonie, c'est en fait une reprise d'un nom qui a été proposé
Michel
au début du
Ventron
XXe siècle
has called this
par
the
un
gate
peintre
or
français
door
qui
of
s'appelle
harmony.
Paul
It's,
Sérusier,
in fact, the reference
qui
is
était tout à
to
fait dans la mystique du nombre d'or
a
et de-
French
de
painter,
ces
Paul
choses un peu
Sérusier, beginning of the last
numérologiques,
century, which
et
was
qui avait remarqué, Paul Sérusier
who
avait
really
remarqué qu'il
believed
y a
in
un
this
nom
golden
pour le rectangle,
ratio.
le
He
rapport
was
de la longueur à la
interested in
largeur,
numerology, and he had
et
noticed
le
that
nombre d'or.
in the rectangle
qu'on
there was a
appelle un
special
rectangle
relationship
d'or,
between length and
et
width,
qu'il n'y avait
and
pas de
the
nom
golden
pour un
ratio,
rectangle
it
équivalent
is
avec
what we
racine carrée
call
de
a
2.
golden
Et il
rectangle,
avait
and there was
décidé
no
de l'appeler
equivalent number with the square root of 2, and he had decided
C'est un
to
joli nom,
call it
mais
the door of
il
or
s'agit
gate
pas
of harmony.
d'essayer
It
de
is a
dire
very
que la
beautiful
racine carrée de
name,
2
but
serait le vrai nombre magique,
it
et de
is not
remplacer
a
la
matter
mythologie du
of
nombre
saying
d'or par la
that this is the
mythologie
real
de la racine
magical
carrée de 2.
number,
Donc,
and to replace the
ça n'est pas non
mythology
plus
of the
un
golden
nombre si
number with the
important
mythology of the
dans la
square root of
connaissance. Et
2.
je préfère, pour
It
éviter
is not
de
so
trop
important.
pour éviter un peu
And
l'héritage
to avoid
mythologique,
the
parler plutôt de rectangle diagonal.
heritage, the mythological
diagonal,
heritage,
c'est
I would like to
c'est
talk
le
about
rectangle,
a
comme
diagonal
sur la diagonale.
rectangle. The diagonal
Car,
rectangle
comme
is a
qui est un
rectangle which
rectangle
you
qui a
build here
un
on
tas
the
de
diagonal
propriétés géométriques
of
très
the square.
intéressantes. On peut faire un tas de
It
choses.
has
La
a number of
propriété la
very
plus
interesting
utile,
geometrical properties.
c'est que
You
quand
can do
vous
lots of
coupez
things with it.
verticalement un rectangle diagonal en deux,
The most useful one
vous obtenez
is
deux petits rectangles
that when
qui sont eux
you
aussi
cut
diagonaux.
it in half, you will
L'utilisation la
obtain
plus
two small
importante de ça,
rectangles, which are
c'est
also
nos
diagonal
feuilles de papier.
rectangles. The most
Vous vous êtes sans doute
practical
déjà
use
demandé
of it
pourquoi
is
on utilisait des
our
feuilles au
pieces
format
of paper.
21 cm et
I'm sure you've
29,7
wondered
cm.
why we were
Eh bien,
using
enfin, vous avez la réponse.
21 by 29.7 centimeter. Well, at long last, you have an answer.
Et
29.7 divided by 21 is roughly the square root of 2, which means that you can define different formats which all have the same shape.
Vous pliez un A4 en deux, vous avez un A5.
A4.
Mais si vous
If you
voulez
want a
plus grand,
small one, you just halve it. You have an A5. But if you want a bigger one,
le A2,
A3,
le A1
A2,
et le dernier, le
A1,
A0, qui par définition
and the last
est le
one,
rectangle diagonal d'un
A0,
mètre carré.
which by definition is the diagonal rectangle of which has a surface of 01 square meters. Find its height and weight. You can now fold it, fold it, fold it, and you're back to 21 and 29.7, which is your A4. This standard was created or legalized in France at the end of the 18th century. Here you have the law which was the 13th of Brumaire, which is the Republican calendar, which is in fact the 8th of November of 1798, and you can see there's a table where you find roughly the equivalent. There's no A4, but you've got A3, which is here, which is called the middle-sized piece of paper, and here you see all the various numbers. All the various numbers are here, and the length 0.42, I think it is, yes, twice 21. Here's the format. So it is a law. It is in fact comes under the tax laws, and it was a matter of defining the price of the tax or levy that had to be paid for an official act, which was like stamp. You had to pay official stamps, stamp duty. And so the price of the stamp duty depended on the size of the piece of paper, and that format made it possible to harmonize. It was the fiscal harmonization with a number of other practical uses attached to it. For example, paper manufacturing, you had an A0, and then if you had an A1, you had to cut it. You don't have any waste. You don't have to cut things which are not down to the same side. It's also much simpler to store it, and so on. Unfortunately, the law, as soon as it was issued, was forgotten, and it was never implemented or enacted. But it was rediscovered or reinvented in Germany at the end of the 19th century by somebody who was called Oswald, and he was an engineer. And there was Walter Portman, who, and this was the work of his life, was to make this public, and he was successful in 1920. And now to finish, not to remain in the idea or dwell on the idea that this is not essential, I would like to show you something which is more up to date. Here you have the first 1,000 decimals of the square root of 2. Very easy. The computer does it very easy, thanks to the Babylonian algorithm. But from a quantitative point of view, we've all understood everything about it. And we could have just left it at that. But then in 1909, a French mathematician, Émile Burrels, raised a new question. He said something to the effect of, would my birth date appear somewhere around here? Well, not like that, but, but this is the question he raised. That is to say, would the figures appear in a very different order all the time? Or would 3, for example, be found more often than other figures? Is there a sequence of 1,000 zeros, one after the other? Are there any such sequences? We don't know. As far as your birth date is concerned, date of birth, you can look. If you find it, good. And if you don't find it, maybe you should simply move on. And how would you know? Well, there you are. Burrell raised the question in 1909 and went back onto it quite a few years later, saying that it was one of the most important problems for mathematicians, and that's where it stands to date. And now, in 2011, we have not progressed anymore, and we don't know really much more on how the decimals are divided. So there is a particularly big mismatch between the simplicity of the definition of the square root of 2 and its calculation and the difficulty of the qualitative behavior of this decimal. The problem appears to be so difficult that it is not sure that we will have the answer in this century. The most accurate results that we have were obtained in 2004. There was an American and French team that made a little step forward on this, but they're very far from having the answers to the questions that Burrell was raising about a century ago.
Sentiamo allora le domande del pubblico.
Let's hear what the questions are from the audience. Today's conference is called The History and Fate of the Square Root of 2. I would like to ask you if there's an example of the use of this irrational number by Bach, the composer. Yes, well, Bach, it is a matter which is rather controversial. Bach wrote something which is called the well-tempered harpsichord. And personally, for a time, I thought that for a time the well-tempered harpsichord was all at the same level, but that's not true. But certainly Bach may have used the square root of 2 because the range, which is well-tempered, is where each note has a constant relationship or ratio with the previous note. if, for example, you have one which is worth 1, the next one 2, to have the octave, and the C will be 1, and D will be the 12th root, and so on and so forth, right up to the square root of 2, which corresponds to the F and F flat. And it's like the devil in music. Now, for example, if I take the telephone book, there are a large number of numbers in it. There's lots and lots of numbers in it, but I see that not all the numbers have the same frequency. 1 is more frequent than 2, according to a logarithmic sequence. At least I think that's what it is. Is this also true for the for example, for the square root of 2, the most probable situation is that there is an equal share. There are as many zeros as ones, as 2s, as 3s, and 4. That is to say, as if you really had a roll of the die every time you have a new decimal. Because there has been, for the time being, no pattern which has been identified. So it's not the same thing as what you were saying as far as the logarithmic series of the figures are. Good evening. Please excuse me for asking a question that might be a bit naive. But if I measure the side of a square, even precisely, I will have measurement x. If I measure the diagonal with the same degree of accuracy, I will also have a measurement, the real measurement. Now, my question is, irrational numbers, are they outside mathematics? That is the sense that they don't express something real, or what are they? I don't know if my question was clear. That's a very difficult question. The question could be saying, is there a square? Is there such a thing as a square? You can draw a square. But is it a real square? It's never really a square, is it? The mathematical work is, the aim of mathematics is to set a distance between the square that you see and in the imagination of an ideal square. And you work on this ideal square and its ideal diagonal, which is going to be the square root of 2. And it's going to be the diagonal is going to be the side by the square root of 2. And this is the strength of mathematics. That is what gives the mathematics the ability to generalize. The fact that you can use it and apply it to very different things, because it is not limited to one problem. On the other hand, you could ask yourself if you can go back to the practical case, and that is the problem of creating models, and that's not really a mathematical problem. And physicists or philosophers, I am sure, would have more to say than me, as I'm a mathematician. That is to say, if I wish to remain a mathematician. Thank you very much. A very beautiful answer, because it helped us understand the philosophical depth of mathematics and also outlined meta-mathematics.
Buonasera. Per semplificare, potremmo dire che...
Good evening. Just to simplify, could we say that especially the square root of 2 has useful and has the appeal of the of being practical, while the harmonic ratio has the fascination of beautiful. Difficult question again. Difficult question. What I really loved about the square root of 2 is not its usefulness, because I'm a mathematician. So for me, the square root of 2 is the intersection of a number of different things, and not only of usefulness. As far as beauty is concerned, I'm afraid I would say things that would not be informed, and I'm not going to say much about it. Thank you. I would like to thank Benoît Rittaud. Thank you very much.